First, a few words of respect for the Ukrainians. Those poor guys who are still fighting for their freedom for ours. Today, I'm going to have the second lecture on ΔQSD. And tomorrow there will be a lab session using a tool that can draw the delta Qs when you type in the outcome expression. So it can do convolutions for you. For example, you can see the nice things when it happens. And there'll be some exercises. So bring your laptops. And for those people who come tomorrow and who are working, that means at least 1 hour, I will give you 1/2 point bonus on your final grade. See how easy it is in this course to get points. So Mathieu will bring presents. So bring your ID card for that. And what else do I want to say about that? Yeah, so it will normally run on any laptop that doesn't have a system that's too exotic. Okay. So this is a tool that the people in PNSol have been developing. It's still not complete. It doesn't do all the system operators, but it does enough operators to do some interesting things. Okay, so today I want to finish and I want to scale up what we saw last time to big systems that have to keep running and not failing. So this is a real thing that has been used for such systems. Last time we saw compositional systems. It's where you bring boxes together and you can compute the performance simply by computing how the boxes come together. So it's compositional. Doesn't always work. In real systems, you have dependencies. So that's what we're going to talk about today. And we're going to talk about multi-level systems. So systems that have to survive in very severe circumstances. So this is the real stuff. This is how these systems are built. Okay, let me give you first a few minutes refresher from last week. And then I will jump in and immediately give the bigger case study. I mentioned it last time, Cardano Shelley, which is an algorithm used in the Cardano crypto platform. So this is an explanation of a real algorithm that's used. And if you want to buy their cryptocurrency, you can do it. And it's going to be partly running this algorithm that I'm going to show you. And this one is not hidden under NDA, so I can explain it to you. And then I will explain shared resources. Now this is sometimes very nasty. What happens if two components are running on the same CPU? And one of them needs a lot of CPU power, then the other one has less. You see, when you have a shared resource, the two components are conflicting or interacting with each other. And we did not do that last time. Last time everything was independent. So, but in real systems, it's not like that. You have them as shared resources. And then I'll do a more realistic example, an iterative query. When you type in something and you get a response back and you keep going. So this is something that people do every day. And then I'll talk about risk management and multi-level systems. This is what happens when you have very big systems like telephone, telecommunications, or power distribution that is not allowed to break down in real life. Okay? So that is also an extension. So let me very quickly give the simple, first a refresher. Okay? So delta Q, which is also called quality attenuation, is a very simple thing. Okay? It's just a cumulative distribution function of the delay. So today we're going to talk about delay as the main thing. Of course, delay is only one thing that you consume. Time is something you consume. You could also consume power or something. But in the lecture today, I'm going to only talk about delay. So there's some probability that the delay will be less than or equal to d. So this is cumulative distribution, but it does not go to 1 because the system has some chance of failing. So there's some limit here that could be less than 1. So this is called in probability theory an improper random variable. And it's usually considered kind of a defect. I know there's a textbook which says this is a defective thing. No, it's not defective. It lets us model failure. Okay? So this models one component. One component, delay. Now we're combining components. Let me go to, so this is a refresher. I'll give you a simple example of combining components. So let me do an example. Okay, so the very simple example is when you just connect two components, one after the other. So the delay is the sum of both delays, of course. But it's not actually arithmetic, because these delays are not numbers. They're cumulative distribution functions. So the total delay is a kind of a sum, but it's called a convolution. Okay? So, but it intuitively corresponds to a sum. And let me now go more example. So here is the example I want to show to refresh your memory. This is a cache memory example. So here on the blue you have a block diagram. It's a very simple thing. All computers are doing this. And so here you have a cache in front of the main memory. So the cache is very fast, but it only has a small memory. When you read, you first check to see whether the word or the block is in the cache. If it is, you return very fast. If it's not, you have to go to main memory, and then you return slower. This you can model very nicely with an outcome diagram. And you use a choice, an operator called a probabilistic choice. So this is an outcome. Between the two little boxes, there's a start event, which is the read, and an end event, which is the return. And other outcomes happen in the middle. So there's three primitive outcomes. Either the cache has a hit, that means it's in the cache. This is 95% chance, okay? It's a very typical number. And then immediately you're done. Or the cache has a miss. It's not in the cache, 5% chance. Then you have to go to main memory. So the miss already has a time between read and main here. And this time is added to the time of the main memory read. Okay? So you have a complete computation here that lets you compute the whole distribution with the three different primitive ones. And it's this formula here. So this delta Q of the whole memory, cumulative distribution, is a weighted sum. So I explained, so semantically this is correct. That's a weighted sum, the hit and the miss. And the miss and the main are added together. But this is not arithmetic, this is a convolution. Whereas this addition is an addition, because only one of these two is going to happen. You're not actually combining two separate things. It's either one or the other. They're exclusive. So that it can be a simple add. Okay? So that we saw last time, and I made a diagram. So if the hit is like this, it's always one time hit. The miss is 1.5, but it's only 5% of the time. And the main memory is slower, it's 4. So these would be like typical numbers. If you combine it, you get this kind of a step function. So that means it's 95% of the time you have less than 5.5 read, and it can be very, very fast. So basically, and then you have some small number which is, sorry, no, I'm wrong. What it's saying is that after 5.5 you're at 100%. So all of them are less than 5.5, and 95% of them are less than 1. Okay? That's correct. Okay, so we saw that last time. So you see how it works. And you build these outcome diagrams, and this lets you compute the behavior, the time performance of these systems. Okay? Okay, here's another example. So we showed examples last time, so we did the semantics. I just want to go very quickly to a more complicated example. This is a more complicated example. There's several things going on here. So I have a cache, as before. When it hits, it just returns. But when it misses, it goes to main memory. But in this example, the main memory is on the network. It's behind the network, it's slower. So there's a timeout circuit here. So you wait for the timeout. But if the main memory is too slow, it times out, and you return a signal saying it's timed out. And that behavior is given by this outcome diagram. Okay, you start with the read, 95% chance it's a hit, 5% chance it's a miss, and then you do a timeout. But timeout is first to finish. You have two things, the read and the timer, okay? And the first one that finishes is the 1. So here you have a first to finish, which this exists symbol. Here it goes to the network, and here you have a timeout event outcome. So here you have the net, that's the going there. Here you have the main memory, but we're also modeled the main memory failure here. Notice this main memory, there might be cosmic rays going in there, and there's a small chance it fails, 10 to the minus 16. So you can model that here. So that's modeling even the main memory failure. So these two together give you the return. So this whole diagram shows you the behavior of that system. And you can compute the actual behavior and the probability of failure. So this guy has a small probability of failure, okay? And these, so the timeouts, this one might time out, you can compute that and see what effect it has on the read. Okay? So I'm not going to do that, but that's but you can do it. What I want to show you now is so that was a refresher. I want to show you a bigger example of using this for designing a real algorithm. So this one is going to be more complicated. The algorithm diagram is going to be more complicated. Okay? So I have to give you a small introduction to blockchain. Blockchain is a very complicated thing, and there's lots of algorithms in there. So I'm not going to give you a whole course on it, but I will give you enough understanding so you kind of see what's going on. Okay? So this is the Cardano blockchain. This is a real-world blockchain, which is used by lots of people. It's one of the big ones, okay? It's smaller than Bitcoin, but it's still pretty big. And it's an open source platform using proof of stake. Okay, so just a quick introduction. A blockchain, in general, it's a software implementation of a ledger, a distributed ledger. So a ledger is an easy thing. It's just a book where you write down financial transactions. Okay, George gave 100 euros to Bob, or something like that. Or Bill bought a field for 10,000 euros, you know. It's just a ledger, and it's something where you cannot erase. They're actual transactions, and they're permanent. And it used to be written by hand, but the blockchain is a piece of software that does it. Okay? Now, this piece of software can be attacked. So it's written, it's completely implemented as a consensus algorithm, so they all have to agree, all the users, on what is the transaction, clearly, and it's distributed. But it's one that's Byzantine, so it's secure. So I'm not going to go into that, but it will resist attacks. Okay? It's used to agree on the correct sequence of blocks. So this algorithm, all nodes will agree that these are the transactions. Okay? So Cardano has invented its own algorithm for this called Ouroboros consensus. Okay? So the way it works, partly, when it produces a new block, it selects a node, there's many nodes on the system, to produce a new block, and transactions can be written on there. And it's random, but it depends on the probability. So not all blocks are equal. Some blocks are more likely to be chosen, but it's a random choice. Okay? So the block producing node is randomly chosen. So this node will produce the next block. That means it has to know the most recent block, because the next block is going to be attached to that one. So the most recent block, you have to kind of broadcast it to all of the potential block producing nodes. See, this is a distributed algorithm, so all these nodes are working together. It has to be disseminated. This is called block diffusion. It's kind of a secure broadcast algorithm. Now, we're going to design a block diffusion algorithm to use with ΔQSD. And we're going to be mostly interested in designing the algorithm so that it's fast enough. Okay? If it takes 10 hours, then Cardano will be very slow and nobody uses it. So it has to run fast on the internet. Okay, so that's the idea. So here's the more precise explanation. So here on the left you have some graph of all of the Cardano blockchain. So each of these nodes is a part of the blockchain. It's a user and it is part of the consensus algorithm. And I picked two random nodes, A and Z, and I I need to do block diffusion. So the block is diffused over all of these. So it takes some time to get to Z. So there's a delta Q there, from A to Z, okay? And delta Q AZ has to be fast enough, okay? What we know, there are certain things we know. Between two nodes that are next to each other, X and Y, we will in some cases know the delta Q on the internet. We also know some other facts like the graph, the block size, the forwarding protocol. We'll talk about that. How do you forward big blocks? So for example, if you forward a big block, you don't forward it all at once. You first ask, am I allowed to go to you, or do I have permission? And if it says yes, then you can forward it. So there's some protocol, okay? So these parameters. Okay, so we're going to design the algorithm, but I'm not going to show you the whole thing. I just want to show you how the outcome diagram helps. So this funny graph on the top is like the design process. It's like the design tree we saw. So you start with initial design, which is one hop. I send a message from A to Z, boom. Might be slow, okay? So you make a TCP connection and you send. But that might not be good, so maybe you want to do multiple hops. So you make a design decision. I want to do multiple hops. And then you see what the performance is. If it's not good, you go back here and do something else. Also, once you're here, you might do header body split. For example, I have a small header and a big body. I don't want to send this huge big block if there's no space on the other side, for example, if I'm not allowed. So the header body split asks first and then it sends the block. So I add that. Also, nodes can leave the network. New nodes can join the network. So that change the algorithm. Also, nodes can select neighbors. There's an algorithm. So this was a little bit like BitTorrent. Huh? It will kind of select the fastest neighbor, in some sense. Okay? So this is kind of the process we're going to follow. But I'm not going to do the whole thing. I just want to show you a particular example. I'm going to show you two pieces. The first piece is very quantitative, number crunching. We're going to actually measure the delta Q on the internet, okay, between two random nodes. So we're going to measure and we're going to do some computations using probabilistic choice convolution, okay? And that's the first part. What is the delay between two random nodes? And the second step, we're going to actually show, and I'm going to show you an outcome diagram that makes a bunch of decisions, okay? And from this diagram, we can compute the delta Q. And each time we add something, we will compute delta Q, and if it's not good, we keep going. If it's really bad, if it cannot get better, delta Q's can only get worse, huh? Delays can only get worse. If it's too bad, we have to start over again. So this is the design process. This is all explained in an article, which you can find here. So if you want some more information. Okay, so first step, we want to measure the delta Q's. This is very nuts and bolts. Two nodes across the internet. We're going to need to do some work. So we need to know stuff. The block size, assume it's from 64 kilobytes to 2 megabytes. The network speed, we're going to measure that. Geographic distance, what distance between two nodes. We're going to assume 3 distances for simplicity. Short, medium, and long. Short means they're in the same data center, the two nodes. Medium means they're on the same continent. And long means they're on different continents. And we will ignore network congestion. So we will first measure this for single hop. And then we will combine to measure multi-hop. Okay? So there's two things we have to do. First, if you make multi-hop, it's a sequential composition. So we have to do convolution. Okay? And then we do random path. Maybe between two nodes, there's multiple paths. So we have to choose one of the paths. So this is a probabilistic choice. So we do weighted sum. So we're going to use sequential composition and probabilistic choice. So that's the idea. Okay, so here's the first step. On the top here, this is measured. Huh? Here we have different size blocks, 64K to 2000K. Here's the delay, cumulative probability, short, medium, long. Huh? Short, medium, long. Same data center, same continent, different continents. So you can see the longer blocks here are going to take longer, of course. The smaller blocks are going to be quicker. Now we do multi-hop. So this is one hop between two nodes on the data center, between continents. Now we do multi-hop. Well, we're going to convolve this guy with itself. So 2 hops means this guy convolved with itself. Then 3 hops, it's 3 convolutions. You'll do this tomorrow in the lab session. So you see, this is what happens. So the 1 hop is the same as before. So this is for 64K. 2 hop, it starts to get a little bit more. And then once you do 5 hops, it starts to get a little bit smoother. You see, it slows down a bit, but you have this kind of curve. So this gives you a good idea of what the average and the variation is of the times. So it's not just a single number, like the company that I named last week, which I will not name, they thought that delays were numbers. That's wrong. Delays are distribution functions. Okay? Here on the right, it's the same thing, but for 1 megabyte. Okay, so 1 hop, 2 hops, so it's convolved with itself. The 5 hops is convolved. You can see when you get to 50% here, it's like 1.2 seconds. Here the 50% will be 3.5 or 4 seconds. It's normal, the block is a lot bigger. Okay? So this is important if you want to know the average behavior and so on. So this is multi-hop. The next step is varying paths. So now this requires some graph theory. We have a random graph of 2,500 nodes. We have picked 2 random nodes, and there's many paths. So we have to somehow do the weighted sum of all of these paths. So this requires some non-trivial combinatoric kind of computation, and it gives you this result. So now it starts getting a lot smoother. So for 64 kilobytes, you can see it's very fast, like 1 second for 50%. 256 gets a little bit slower. And so the 2 megabyte, 2000 megabyte ones, no, 2 megabyte, 2000 kilobyte, they get like 3 seconds, okay? So this gives you the behavior. See, it's very steep in the beginning, and then it kind of a little bit flattens out. So this is all computed using the stuff we saw before. Okay. So now we have all this stuff. Now we design the algorithm. Okay? And so we get diagrams like this. So I will explain, this is a big diagram with lots of stuff going on. Okay, so what this diagram is doing, first I tell you, but then we go and look up. So this one is obtaining 3 blocks from the fastest neighbor, where I request permission before transmitting, and blocks are divided into head and body. So that is the algorithm that we're doing here. So if you know all these little primitive delta Qs, you can combine them using all to finish, first to finish, and so on. Okay? So let me now explain them. So just to refresh your memory, we're using 2 operators here. All to finish. So the end event means that all of the outcomes have occurred. First to finish, it's only the first one. Okay. These diagrams look a little bit different from the previous ones because I'm taking them from the paper. This is coming from the published paper. So here's how it works. So we can look at how this outcome diagram works. So on the left, you have this, these outcomes have these little annotations. So there's a permission, P header, T header. This is transmission. That means you're allowed to transmit. You ask for permission. So from Z to A, you get the authorization. And here, the B is the body. You have the permission, you ask for permission to transmit the body. Okay? And this one. So here, I'm getting 1 out of these. This is a first to finish. But notice that this is an all to finish. So this is the first block. If I'm allowed to do the first block, then I ask for the second block. I ask permission. If I'm allowed to do the second block, I ask for the third block. So when I come here, I actually am allowed to do all 3 blocks. And for each of the 3 blocks, I actually do a first to finish because I'm going for the fastest one. I send to multiple different neighbors, A1 to AK. Okay? So first to finish is only looking for the fastest one. So this little red rectangle here. It's the fastest one. Here also, the fastest. So all these things have to happen for this outcome to finish. So this outcome diagram implements this algorithm. You do a permission request for each block before you authorize the transmission. You do the header, so this is header, before you do the body. And you're doing 3 blocks, but you're only doing them, so each is looking for the fastest neighbor, and you're doing it for 3 blocks. Okay, so that's already a fairly complicated algorithm. So this is a big outcome diagram. So this is what the guys from PNSol did when they designed this algorithm. With this, we can actually predict how fast it will be before building it. And the real distribution functions, that means it's not just numbers, that means we really get a good idea of how it works. Okay? Okay? So the resulting diagram correctly models causality and performance. Okay? Now this is complicated, but you could build a tool. But so far we don't have this tool. But that's something we want to do. Okay? So this gives you an idea of how you scale the approach up, that you can really predict performance of real systems. So this thing was really used for Cardano Shelley. Okay. Okay, so that's the second case study here. Let me now go on to the next step, which is dependencies. So this is a little bit more than just connecting blocks together. Here the blocks affect each other. They are dependent. Maybe they're using the same battery, or they're sitting in the same room, so they have the same temperature, or something. There's some dependency between them. Okay? So a real system, any real system, most of the parts are independent. In a processor, most of the transistors are working independently, but sometimes they're not. If 2 transistors and there's like 2 wires going next to each other that are both outputs, well, they're going to kind of interfere, and there we have a dependency. Okay? So most of them are independent, but sometimes you have to add dependencies. So that's very important. So real systems have some dependent parts. A few dependencies are added. For example, 2 people use the same database. Well, they might interfere. That if the database is busy with one, it might slow down the other one. Okay? So I'm going to show you examples of this. So here the theory is not so complete yet. I'm going to show you some examples. Then I'll show you a bigger, kind of neat example, iterative query. And then I will go to multi-level. That's kind of the biggest thing to make systems that really survive in really nasty circumstances. Okay, so this is real stuff. Okay, let me show you first some shared resources. Okay, so shared resources. So first I want to kind of define what is a shared resource. So, okay, so the computing of delta Q is simple if the components are simple, are independent. But a real system has shared resource. What is that? Well, we define a resource as a part of the system that can be used by 2 other parts. Okay? And there might be some limitation in how it's used, but it can be used, it kind of connects to other parts. And in the model, it means we have additional variables and equations. So we have to model this dependency. So basically, we have more complicated equations to solve. It's not just convolution and weighted sum. You might actually have recursive equations. The equations can get complicated, okay, when you model dependencies. So you have some kind of a solver. So things get more complicated. So I'll show you an example. Now, after years of experience, the people from PNSol noticed there's 2 kinds. Resources, they kind of classify. What kind of resources exist? So there's actually 4 kinds of resources, and there's 2 properties that a resource can have. It can be ephemeral. Ephemeral means you can use it now. And if you don't use it now, it's lost. Okay? So the sun is shining now. And if you don't use the solar power now, tonight there's no sun, okay? So it's ephemeral. But if it's not, it doesn't have to be ephemeral. A battery, if you don't use it now, the energy is still there. You can use it later. So it's not ephemeral, okay? So that's ephemeral. Also, there's this notion of a threshold. Sometimes there's a maximum. If you try to use more and more resources, what happens? There's two possibilities. Either the resource kind of degrades, and that's not threshold, or it just collapses. So if you take a power line, and you pull more and more power out of that socket there, at some point, I mean, I'm pulling thousands of watts, more power. At some point, the circuit breaker will trigger, and the power drops to 0. Okay, boom, threshold. Exceeding a particular limit causes the delta Q to become failure. So it fails immediately, 0. Okay, but if it just degrades, then there's no threshold. Okay, it's a specific difference. So things like power is typically threshold. Batteries also are threshold. If I have a battery and I'm taking energy from it, at some point the battery runs out of energy, and so the energy coming out drops to 0. Okay, the power drops to 0. Threshold. Okay, so that makes 4 different kinds. So this is just for information. Afterwards, I'll show you examples of different kinds. So an example of an ephemeral resource with no threshold. Well, a network connection. So I'm communicating on a network. Well, maybe there's congestion, too many people. Well, the failure rate's going to increase, but it doesn't drop to 0. Okay, it just decreases. So there's no threshold. Okay? So when there's a lot of congestion, the performance goes down, but it doesn't drop to 0. So it's ephemeral. If you don't use it now, the network, then that bandwidth is lost. Maybe there's new bandwidth later, but the bandwidth available now has to be used now. Okay? So it's ephemeral, but not threshold. You can also have ephemeral and threshold. So this is something which is the working set of a process. So this is maybe something you haven't learned, but if you run a process in a computer, it takes a certain amount of memory, RAM memory, and the process has an active memory size. Okay? So maybe it needs 2.5 gigabytes of RAM to work. That is the working set. But if the process does more and more work, it might need more RAM. But what if it needs more RAM than actually is installed in the computer? Okay? What if I only have 16 gigabyte installed, but my process has a working set of 25 or even 19, a little bit more? Okay? What then will happen is that the system will thrash. It actually might still keep working in some sense, because it tries to do swapping. It tries to move pieces of RAM onto the disk and move pieces of the disk into the RAM so that the RAM is always usable. But if the working set size is bigger than the actual amount of RAM, this is not really going to work very well. And the system will maybe be 10,000 times slower. It will maybe essentially be stopped. Okay? So this is a threshold. So don't exceed the working set. So the working set should never exceed the size of the RAM available. Well, that's a threshold resource. And another example which I gave is the electricity at an outlet. You draw too much power, well, the cables cannot handle that. There's a risk of fire, you know. So the circuit breaker trips, and power drops to 0. Okay, so threshold. And it's ephemeral. If the power is there now, and if you don't use the power at this instant, that power is not, I mean, there may be other power, but that power is only available at every instant. Okay? Some examples of non-ephemeral thresholds. So let me do this one first. Non-ephemeral threshold. Typical is a battery, which is not recharged. So I have a battery, so like in this stack, there's no power, battery. And I'm taking power out of this battery. So it's supplying energy at a particular rate, power. And it keeps doing that until it's empty. And once it's empty, it stops. Power drops to 0, okay? So that's a threshold resource. And it's not ephemeral, because if I don't use the power now, it's still there later. It doesn't go away, okay? So it's not ephemeral threshold resource. And you can also have non-ephemeral, non-threshold resources. These are a little bit trickier. For example, wind energy, a wind turbine with a battery storage or some kind of storage. So the battery is always being stored, always. So if I pull more and more energy from this thing, okay, the battery can kind of go down, but since this wind is, we're assuming it's turning mostly continuously, it doesn't actually go to 0. It will go down quite a bit, but always some power will be coming out, okay, because there's the wind. On the North Sea, the wind is basically there 24 hours a day. Okay, so that's some resources. But now I want to give you some examples. Here's a very simple example that happens all the time. Congestion. So here we have a router, which is a component, and we have message streams coming in, 2 message streams, going to the same router, and they're using a shared network on the output. Okay? So each of these message streams has a load. Remember, we use the letter A for the applied load. So the total load going into the system is the sum of the loads on the 2, AX plus AY. And remember we saw that the component can be modeled as a Q, and that the performance depends on the applied load. And each component has like a limit, of course, the load equal 1. Huh? And if the load here starts getting close to 1, it's going to start dropping messages. So you have, that is what congestion is. Huh? Packets are being dropped. Huh? These messages are packets. So the Q model we showed before, it is a nice model for routers. Okay? So if AX plus AY is greater than 0.8, that doesn't even have to be 1, then some messages are going to be lost. And the bigger it gets, the more that get lost, congestion. But it won't go down to 0, but it will go down. So this is an example of an ephemeral, non-threshold resource. And here's how you can compute it. So you have these 2 numbers here coming from the system. So you have this extra equation. A is equal to AX plus AY. And you have A, which is an argument of this delta Q, and these 2 other A's are coming from somewhere else. So you have an extra equation in your system, and you have to solve that. So it's not so simple anymore. You may have recursive equation and so on. Huh? Okay, so that's a simple example. Here's another example. Very simple too, very common. Shared CPU. So here you have 2 components working, but they're running on the same processor. Okay? The same processor core. And each one of them is using a particular fraction of the processing power. So assume that they're both running nicely. So the sum of the 2 is equal to 1. It could be less. Let's say it's equal to 1. That means together they're using 100%. Okay? But maybe one can be using more than the other. This depends on certain things. It depends on the load coming in here and so on. Huh? So you get this extra equation, because you don't actually know what the values of C1 and C2 are. Okay? It gives an extra equation, and you have to solve for that. So again, you get an extra equation, things get more complicated. Okay? And I'll show you an example in a minute for this. And here's a third example with a very weird constraint, nonlinear, strange one, but it's very realistic. A shared cell tower, very common thing. Okay? I have 2 carriers. They're sharing this cell tower for mobile cellular phones. And each one of them, so the contract, they have signed a contract with this tower company. Each one is guaranteed to get at least 50% of the tower's capacity. Great. But there's more. If one of them is using less than 50%, then the other one is allowed to use the extra capacity. Hey, that's nice, huh? Fringe benefit, huh? So if carrier 1 uses 30%, Carrier 2, it could easily use 60% or even 70% of the capacity, because carrier 1 is not using its whole piece of the pie. Huh? But, snake in the grass, if carrier 1 now suddenly says, oop, I need more users are attached, immediately jumps to 50%. Carrier 2 has to immediately drop from 60 to 50%, and its packets will be lost. Okay? So the load for carrier 2 will decrease. So there's some weird dependency between the two. You see that, huh? If each one of them is low, then the other one is kind of free. But when each one of them increases, it kind of hits the other one. So very strange. So I tried to model it here. So this is my current best guess, okay? So assume each carrier requests a load. So AC1 and AC2. And each of these loads are between 0 and 1, let's say, okay? And the shared tower will then grant, will say, okay, you're allowed to use something. So it only gives BC1, which might be less than BC2. And the total load of the tower is the sum of those two, which has to be less than or equal to 1, let's say. So we have these constraints. If the load A on C1 is less than a half, less than or equal, then it gets everything. BC1 is what it gets. It gets everything it asks for. And if the load on C2 is bigger than half, okay, sorry, if the requested load is bigger than half, then C2 might get more than 50%. So if C1 is actually a lot less than half, BC2 might get more. Huh? So if C1 is 0, then 1 minus C1 is 1. Okay? And if C2 requests 1, it will actually get 1. Okay? So there's a constraint connecting C2 and C1 here also. And the final one is if they're both requesting a lot, how do we divide it between them? Well, maybe we're assuming they get kind of equal priority in that case. Each one gets a half. But maybe this one is paying more, so it gets more. But we're assuming that they're equal here. So this is a complicated dependency, yeah? Okay. So if you want to solve, if this is part of your system, and you want to predict the performance, these equations are part of your solver. You can see it's starting to get complicated, huh? You see that? Okay. Okay, so those are 3 examples. So you see the kind of things you can model. They're very normal kinds of things. But now, let me give you now a real example that I want to work out completely. Okay? Which is an iterative query. And we're going to compute the equilibrium load for this beastie. So this also is a very simple example, actually. It's conceptually a very simple thing. Okay? So you have 2 components, a user and a server. And the outcome diagram is this funny cycle thing. So what is happening? So I'm sitting in front of a computer. Okay? I'm the user. The computer is the server. I type. So I make a query. I'm typing something. The browser accepts, it does some stuff, and it displays the result. Okay? And I see the result. And I see the result, and I type something else. This is called browsing the web. Huh? So I see the result here, and I think, so the user is thinking, and eventually I will type something else. And this goes on forever. So the user sees something and types something, and the server will get a request, display something, and so this thing cycles around forever. So this is this iterative process. So this is a neat thing, huh? It's a very common thing. So what is the performance of this going to be? Okay, how fast is this going to work? Okay. So this models many human-computer interactions. You can see how interesting and useful it is, huh? So let's compute the delta Q for this system. So there's 2 kinds of outcomes. So there's the OS, so where you get the query is input, and the request is output. So Qn and Rn, so n is the iteration, huh? And then you have the opposite one, where I get Rn, and I type the n plus 1 query. So I go to the next iteration, so it's Rn Qn plus 1. Okay? So I have an unending sequence of these guys. So it starts with me typing, and then it starts circulating like this. So I have an unending, unbound sequence of outcomes, and these are causally connected. So the less than symbol is causality. Huh? So as this thing circles around. So what's the performance of this thing? Well, we have to write down some equations, which I will do. Okay. So we have two equations. So we have the delta Q of the user and the delta Q of the server. So we have to make some assumptions. Okay. The server will assume, like before, that it's some generic component. So the server, delta QS, is a function of the load A. Okay? So the load is how many messages are coming in per second. Okay? So the load is actually a function of the total delay. The total delay is delta QS plus delta QU. Actually, this is just a kind of way of seeing. I'm not actually adding them like this, huh? So, but we'll see. So what happens is, at any instant, I will have one particular delay here, one particular delay here. So the delay is a sum of them. Okay? So this is probability cumulative distribution function. So the load is what? The load is 1 over the delay. If the delay is 0.1 seconds, then there's 10 queries per second. It's 1 over the time. It's the number of queries per second. So we use the probability density function. So how dense is it? How some delays might be more dense than others. So we take this distribution function and we make the derivative, which gives you the overall density function. So this is a function of the delay, but it's also a function of the load, because each of these guys is a function of the load. Okay? So we're going to make this integral here. So the density is divided by t. That gives you the instantaneous load for that particular value of t. Okay? So you have to have the expected value of 1 over t. So you have this integral here. Interesting, huh? And it's recursive, because there's an a here and there's an a there. So this is the typical kind of equation we have to solve. So let's solve it, but let me make some approximations on this. Okay. So let's first of all say the user is always doing d seconds. It's thinking the user is doing very fast, 1 second or 2 seconds. It's always constant. So that's the user. Let's say the server is just as before. Remember we saw before? Let's assume the load is low. So the server is not overloaded, okay? So that means it's very low load. That means, if you remember the diagram we saw before, the server is going to be like this. You have this small delay, which is AS over 1 minus A, and then you have the actual service time, this uniform distribution, huh? So combining these two, it's a convolution, huh? Because I said plus, but it's a convolution. So this is, you're basically delaying this by d seconds. If you do the convolution, you get this. And then I make a derivative. So the density is, here it's non-zero, but here and here it's 0. So the density here is 1 over s, because the volume of this thing is 1. So here you have d plus as over 1 minus as. Okay? So that is the density function. Now we do the integral of this guy, divided by t, from 0 to infinity, but it's only non-zero between these two numbers, so we don't have to worry about this. If you work out the integral, and it's not hard, you get this. It's a natural log. So the load, so this is also recursive, because I worked out the integral, but I haven't actually solved the recursive equation. So the load is equal to 1 over s times the natural log of 1 plus 1 over ds plus a divided by 1 minus a. So this is assuming the uniform. That's an approximation. So this is actually interesting. Notice we have this ratio here, d over s. That's interesting. thing. This is a dimensionless thing. This ratio is the user time divided by the server time. How fast am I compared to the server is what it's telling me now. Also, the server time is important for the absolute value here. Okay, so how do we solve this? Well, let's make a graphic solution. This is actually a very nice way. We have two things, two lines, okay? So here on the horizontal we have the A value. We have vertically, we have this complicated function. But it depends on the value of D and S. So we have a family. If D and S are equal to 1, we get this kind of blue-green line here. If D is equal to 2, it's this line. If D is equal to 5, it's this line. And then the black line is the line where A, the result is just A. So A is equal to that, is the intersection of these two. So you can see what happens when you increase D. For very low D, so the user is very fast here. It's typing like a maniac here. So the limiting time is the server. You can see the overall load is 0.57. Okay, that's fast. So it's mostly the server. But if the user slows down a lot, if the user now is very slow, it's 5 seconds, the overall speed is going to slow down a lot. And so you can, the intersection gives you the thing. So this is kind of back of the envelope. Of course, the solver can do this, and it can be complicated and so on. But this gives some intuition. So ds is the user versus the server speed. So fast user, slow user to fast user. So you can see as the user slows down, the performance goes down. So this is what we get when we approximate using the uniform distributions and a constant user speed here. So this is using these two approximations. Now, if the user is changing, if the D is actually changing, then you can actually see this curve as moving up and down. If the D is changing slowly, then you can still use this approximation. So for the user starts speeding up, but it will never get faster than this, because you have to always wait for the server. Okay? So that's interesting. And you can see, therefore, how this nonlinear behavior translates into real computation. So you can actually see this as some kind of convergence also. If you start with if this system starts running at any speed, it will eventually converge. So if I have any value of A here, I'll take this one, and I find the value of this function, then this corresponds to the following value of A. So if I make the horizontal line to the black line, this gives me the new value of A, actually. So this new value of A, I can go up again to the function again, and so on. And you can see it very quickly converges. So this system is pretty stable. It's not going to be oscillating or anything. It's going to be converging very nicely. Okay. Now, other systems might oscillate, but this one is actually pretty stable. Okay. Okay, just a few words on measuring load. So load, we have measured as the number of events per second, okay, as a function of time. How many requests per second? But you could also look at it in the other way. What is the inter-arrival time? So usually the load is work done per unit of time, okay? The work done, so we're assuming that each event is 1 unit of work. So if we have 10 events per second and we wait for 5 seconds, that gives us 50 units of work, okay? So the work is the rate times the duration. That means you can use averages, okay? A rate A1 for duration D, followed by rate A2 for duration D. It's important because you don't have to worry about things like harmonic means and so on. It's not like computing the averages of speeds. Here we're computing average amount of work done, and that's something you can actually add and subtract. Okay. So a final point. So here's another example, variation. Let's say we have back-to-back servers. You put two computers, and they're kind of feeding each other like that, okay? And they have different speeds. And this also happens with humans, huh? And this is a real-world thing. If I have two human teams that are feeding each other with things, collaborating human teams, one of them might be faster than the other, okay? So S1 and S2 are not necessarily the same. It seems that the smallest one is almost all the waiting messages will be queuing up there. The slow server sets the pace. Makes sense, huh? So the slow one is the one that determines it. The fast one is not going to make much difference. So that's something you can compute, huh? So if you have a slow and a fast one, making the fast one even faster, it's not going to do anything. You have to make the slow one faster. Okay. Okay, so there, I will now stop on the shared resources. So this gives you some idea, and the approaches I tell you now, you can actually use them in real-world systems, huh? Okay, so now we'll make a break, and then I will pass to real systems that have to survive for a huge amount of time, and how do you build those? Okay. So then we go to the third piece. So, but let's make a small break. And that's not good, okay? And it can get really, really bad. So this is a kind of overload situation. And there's some hierarchy here. So we have to be really careful how we build the system. And this really affects how you build the system. So we have to look at multiple timescales, as we'll show in a minute. Okay, so here's the idea. So the black curve is delivered delta Q. So this is what the system is actually doing. And the blue one, here it's just a step function, is the required delta Q. So you can see delta Q1 is completely to the left. So we're good, okay? There's actually a slack. The slack is this little, we have a little, it can be, probabilistically, it can do a little bit worse and still be okay. Whereas if we increase the load, for example, we might get delta Q2. Now we're intersecting the requirement, and there's some probability of the intersection. So you see here, this red part is the probability of that we're between here and here. See, so there's some probability that we are in that part. That is the hazard, okay? So slack is good, and hazard is, well, I mean, it's maybe not bad, it's realistic, and we have to worry about it. So there's some concepts here. Let me define, there's some terminology in risk management. So these are the typical terms. So here we have in the black delivered delta Q, that's what the system is doing, and here the blue step function is the required delta Q, okay? Notice there's some intersection here. So we have three concepts. First of all, the probability that we have a problem. So if we're anywhere in this orange area, it's going to be a problem, huh? But that means that if we're between this part and this part, then we're part of this part of the curve. So the probability of being in this part is P1 minus P0. Okay? So that is called the hazard. Hazard is the probability that we are not satisfying the required one. And the impact, boom, is the cost we pay when that happens. So the bigger the impact, the worse, huh? So the impact could be a bomb falling on your house, or it could be a small pebble falling on your house. Different, huh? So the impact is the cost. Now in our scheme, cost is delay, huh? But in general, cost is anything that is like a thing that you don't want, huh? That maybe you will have damage to the house that has to be repaired, and that costs something. But in our scheme, delta Q is giving delay. So the impact, which is the cost of the problem when it occurs, is a delay, a time. Okay? So it's a function of where you are here. Huh? So when I'm here, it's very small cost. When I get up to here, it's a very big cost. Huh? Because here the system is going to be a lot slower than the requirement. Okay? So the risk then, in the terminology, is the hazard times the impact, okay? And in general, it's how much on average you pay, is what the risk is, huh? So in this case, it's going to be basically the volume of this orange box here. So it's an integral, because for every value of p, you have a different impact. So you have to do the integral of I of p, so I is the impact here, dp. So you have these little possibilities, huh? So for some values of p, you have very low impact, for some you have high. So in some sense, this is like the average impact, which is the risk. This is the expected cost that you pay. And here, it's the expected delay. So we expect this system to have the delay, which is this orange part, on average, okay? So that's this integral here. So the risk is the expected cost that you pay because of the problem. Okay, so that's just to get the concept right. So how do we build the system? So this is something you can compute, huh? So you have these hazards. But now you have different kinds of hazards. Hazards that have low impact, hazards that have high impact. So here we have a kind of categorizing these different hazards. And in PNSol they categorize 4 or 5 orders of hazards, from simple ones to harder ones. Okay? So the lowest one, okay, is causality. So here is so the system, if it's causal, it's going to work. So this is very, very nice, okay? The only way the system can not work is so if causality is respected, it will work. So that's a very simple kind of order hazard. It's essentially no hazard, huh? The first order now is because of capacity. So will it be within requirements at expected loads? Constant average load. Constant, very simple. So this is very linear superposition. So basically it's low, the low load. And now if we increase the order, it gets worse. The second order here, this one is starting to get worse. This is scheduling. It means the system will behave well, but you have to do something. You have to schedule things. Sometimes you have to change the order, move big tasks here, move small tasks. And if you do that, then it'll be okay. If you do scheduling, the system will still be okay, but you have to do something, okay? So that's already a dependent one, but it's reasonable. But the final two ones are the nasty ones, order 3 and 4. So this is internal correlation and external correlation. Internal correlation is basically the system shooting itself in the foot, and this happens a lot. Let's say your system has some maintenance routine, and at midnight it does an HTTP lookup, but all devices are doing that, so the system overloads and it crashes. Ta-da! That's pretty stupid. So that's an internal correlation effect. The system is, because of internal effects, interactions, it has bad behavior. And then the final one is external correlation. This is extreme behavior users. This is the most important one that you have to handle. When you have a telephone system, telephone communication, when there's a natural catastrophe, a hurricane or a huge fire or something, everybody's going to pick up their phone, right? So the telephone system will be incredibly overloaded. So what's going to happen? We want the system to manage that, to do something reasonable in that case. Okay? So this is the most important one. Okay? So orders 2, 3, and 4, it gets more and more complicated, and the order 4 is the one I want to spend most time on. Okay? Okay. So this is now I'm going to go to the final discussion in ΔQSD. How do you build systems to handle extreme hazards? This is where the multi-level design comes in. Okay? Okay, so a little bit of context. Before, we saw how to design systems with predictable performance. Fine. Outcome diagrams show causal connections, very nice. Dependencies are added, very nice. This works when the systems have very limited perturbations. Okay? But it's not good enough if the system has to work in all circumstances. Okay? Okay, well let's add defensive mechanisms in the system, lots of checks and so on. Doesn't work also. Defensive programming is not going to work. The only technique that actually works and that is used is what's called a multilevel system. That means you need to build, when you have your system, a second system which is outside of the first system. So you basically, and in general case, it has to be a hierarchy. Okay? So there's not very many platforms that handle this. Actually, it's very interesting. The Erlang OTP platform allows you to do something like this. So that's very rare. Huh? Okay, so you have to build a hierarchy. Okay? Okay, so let's discuss a little more what's going on here. So we're thinking, the idea is we have overload situation, okay? Hazard orders 3 and 4. Now, we want the load to be small, less than 1, but it's not going to be. It's going to become high, okay? So we cannot avoid it. So that's the first principle. You cannot avoid the high load. Things get bad very long. If we wait long enough, because of fluctuations and because of correlations, we will certainly have a situation when there is overload. Now, some industry solutions say, let's just over-dimension the system, but this is extremely expensive, and it doesn't really solve the problem, because the over-dimension is usually not over-dimensioning the right piece, so the problem will still occur, okay, even though it's very expensive. So this is not the good solution. So the right solution is to have a system with multiple levels, and each level handles a different time scale. Okay, so you have your basic system, which is doing its work, and it gets overloaded. Okay? Now, above that, you will have another system which observes the first one and handles and solves the problem, but at a different time scale. Okay? So let's show that a little bit how that works. So this is the basic idea. Okay, so here I have my system. So here's the system I built. Base system, guaranteed functionality is fine. Now assume this system overloads because of order 3 or order 4 hazard. So order 4 is the worst, but even order 3 is nasty. Yeah? Order 3 can be removed by design, but not always, because the different parts are done by different people. So they will have both of them. So you have 3 levels here. In this diagram, I have 3 levels of fixing the problem. The task level, the configuration level, and the system modification level. So the task level is you're actually changing the behavior of the tasks inside the system. And this can be done very quickly. For example, you can reject tasks or prioritize in a certain way or do something very quickly. So in seconds, so in a very quick time you can do that. But this might not be enough. So you may have to completely reconfigure the system. So basically start it up again, but in another configuration. So this might take days. So the system stays basically the same hardware and the same software, but in a completely different configuration. This can take a long time, and it might take human intervention. And if this is not enough, you actually have to modify the actual system, redesign the system, and of course that can take a long time. So this is a permanent change, okay? So to be a little bit more detailed, and then I'll give you some examples of this. So you start from a base system, and then you add levels depending on the severity of the problem. Okay, so the base system already, it has to obey 2 rules. First of all, when its system is overloaded, the system may start to behave very badly, clearly, yeah? Maybe it's just rejecting all the packets. It may be very nasty, may be behaving very badly, but it should not break. That means if the load reduces again, the system should start working again. So the system should weather the storm, in a sense. Huh? That means, or if it's a boat on the sea, if there's a storm, the boat might get tossed everywhere, but it will not actually sink. And when the storm dies down, the boat can continue its journey. Okay? If you know Latin, this is actually the motto of the city of Paris. Do you know that? Fluctuat nec mergitur. You ever heard of that? It means it is tossed but does not sink. So the city of Paris has this as a motto. And what it means is that the city has gone through many, many attacks, stresses, problems, catastrophes. But when the catastrophe goes away, life goes back to normal. And this is very important. So systems shouldn't be built like this. That means you should never have an irreversible change. And the second rule is, when the system is overloaded, there should be some guaranteed minimum functionality. So there should be some packets that pass. Maybe there's a very small number of high priority packets. But it should not be zero. It should be non-zero. There should be some way of still accessing with minimum functionality. So those are the two rules for the base system. But that's not enough. This will allow the system to survive, but it will not thrive. It will not obey well. If you want the system then to obey well, you have multiple levels that take longer and longer and longer. The task level, basically, the system is handling many tasks. You can drop non-essential tasks. You can stop admitting new tasks. You can also kick out tasks already in progress. Everything to reduce the load, prioritize. This can be done quickly. This is only a temporary solution. The second level is configuration. You use data center elasticity. You use ability to allocate more nodes to the system. You use techniques like software rejuvenation. You put a human in the loop, where the human is actually helping to manage the system. So you do something, but that takes longer. But that might still not be enough. And on the final level is you actually have to redesign the system. You have a permanent system change. You add really new equipment, you redesign. And this might be very long. For example, there's a fire, the system is destroyed, a nuclear accident, or something called a Carrington event, which you can look up. When this occurs, when the Carrington event occurs, the internet will be destroyed. So you can look it up on Wikipedia. And one of these occurs every few centuries. So within and the last one that occurred was in around 1860. This is not, I'm telling you a real thing here, so you can look it up. So it's basically very powerful solar flares. In the 19th century, these solar flares caused sparks, visible sparks, to fly at the stations of telegraph operators. That's pretty strong, huh? If it happens today, the estimated damage would be 1 trillion euros. It's a lot, huh? Most of the internet would be destroyed. And it's going to happen. In fact, a few years ago, there was a big solar flare, but it missed the Earth. Someday it might hit the Earth. So how do you build the system now? So let me now talk about actually building the system. So here's our base system. This is what we talked about so far. Everything we talked about so far is this inside this box. And it satisfies some requirement, some specification called the QTA, Quantitative Timeliness Agreement, what it does and its limits. So we saw how to design it. I showed you some ideas. What happens if this system is so overloaded that the QTA is no longer satisfied? Some huge hazard has occurred. Okay? So that's the problem we want to solve. So how do you solve it? You have to build a system like this. So here is a multi-layer system. So here is our base system. This is the previous one, system 1. Okay? System 1 is doing the work. It's working normally. It's satisfying QTA 1. The other systems, normally, they do nothing. They're just sitting there. And they're monitoring. System 2 is basically observing system 1. Now, what happens is, at some point, system 1 has a problem. It's super overloaded. It does not satisfy QTA anymore. So there's a QTA 1 breach, and system 2 is notified of this. And now system 2 can take over. Now it's system 2 that's working. System 1 is drowning, okay? It's satisfying the rules. It's not sinking, but it's not doing anything. something useful. So system 2 takes over. It may do several things. It may reconfigure system 1. It may replace system 1 by another system and then resume it, okay? It may do part of the work that system 1 did, okay? So system 2 is doing that. But that can happen recursively. System 2 may also may not be able to fix the problem. Then we have to escalate system 2. So the QTA 2 is something like system 2 is able to satisfactorily fix the problem. So if this is not true, then we go to system 3. Okay, so this is very theoretical. But let me show you a real example of this in a minute. So like we said before, so this again is system 1. So it has two special connections. The breach, that when it breaks, its requirement, and then some management, resume operation, okay? So you need to build the system in a special way. You have to have some kind of observation points built into the system for detecting breaches, and it has to have some kind of a management interface. So you have to build these two pieces into the system. Huh? It doesn't happen by magic, okay? And then it follows the two rules we said before. It can behave badly, but it does not break, and there's a guaranteed minimum functionality. Okay, let me now show you an example of this. This is an example that's very common, everybody knows. A supermarket, okay? So we're designing a supermarket chain. So I'm Deleuze or Carrefour or something. Huh? So here's a supermarket. And the users, the consumers enter here, the customers, they collect stuff and they queue up at the cashiers. So these are the cashiers, they pay and then they leave. Okay, collect merchandise, queue up. The QTA for this is that there are less than 5 customers in line at any cashier maximum. Okay, so that is the QTA, let's say, for this supermarket. And if there's more than 5 customers in line, the QTA is broken. So what happens then? Well, then this is not enough. We need a higher level system. So the manager, the higher level system is here, okay? So here's the supermarket. 5 in line, as long as line is less than 5 customers. If you have a breach, then it goes to the second level. The second level is not a supermarket. Typically the second level will be the manager of the supermarket. Huh? And that person has, so this is the story event. You have some choice here. Huh? For example, you can open another cashier. Maybe they're not open. Or maybe there's a self-service section that's usually closed. You open it. Or maybe you open the bar so people will go drink coffee and not go to the line. Or maybe you're in a panic and you set off the fire alarm. Everybody runs outside, okay? Maybe that's not the best solution. So this is basically a local reconfiguration of the supermarket. This will recover QTA1. So you see, this system and this system are two separate systems, okay? And this one can work even if the first one is not working, okay? But it's not enough. What if this does not solve the problem? What if there's nothing you can do here? It's full and you really can't do anything. So there's a QTA2 that the number of violations of QTA1 is less than half the time, for example. But if this is breached, then no matter what this guy is doing, there's too many problems in QTA1. So then you go up to an even higher level. And now we go to the management of the whole supermarket chain, okay? Okay, the big boss, the CEO of the chain says, ooh, problem. We have to solve this problem, okay? Now we have to do some kind of a global reconfiguration. So there's some group of high-level executives get together and they decide on a problem. So the decision might be to build a new store, closely, to do a market study and build a new store, or to increase the size of the store or something. Or to increase the prices, which will reduce the number of clients, but maybe the profits will still increase, okay? Whatever they decide to do. So you can see that each level will escalate the solution. You can see each level happens at a different time scale. So this one is at the level of seconds to minutes. This one might take longer. Before the manager realizes there's an issue, and redoes it. This might take 15 minutes or half an hour or something. This one could take weeks or months. So you can see that each level is essential, and each level happens at a different time scale, and each level is independent of the level below it, okay? So this is how you build really robust systems, okay? Okay, well now we're getting to the end. Let me make you now some conclusions on ΔQSD. So this is an approach. So I'll talk to you about the advantages and the limitations. So advantages, your design doesn't have to be completely specified. Even if you know only bits and pieces, you can still compute performance. And top down and bottom up. At any point, you can see whether the system is feasible. If you compute negative delay, it's not feasible. At any point, you can have latency and throughput under high load. No assumptions about the system state. So ΔQSD, the outcome diagrams, they are observational. They don't actually look at the system's internal state. They don't. So it's not like UML. It's a very different approach from UML, okay? And also, it's stochastic. So this is good because the world is full of variability. Now, it's not perfect because the CDFs is only giving part of the information of the variability. But in practice, it actually works well. Okay, so experience shows that this approach of the CDF is a sweet spot. It gives good results. And if the pieces are independent, it's accurate. And if you connect components and they're actually independent, then doing convolution is actually giving you a perfectly correct answer. Okay? So the design is factored into three parts: compositional, dependencies, and multilevel. Okay? And with this, you can build almost any system that can handle any kind of a load situation. Okay, so that is the positive side. Now the limitations. So the approach is not magic. So first of all, you need valid inputs, garbage in, garbage out. You have to know the requirements. If you don't know them, you can't do anything. You have to know the behavior of components. If you don't know it, you can't do it. You have to know what are the dependencies. If you forget some, your results will not be accurate. If you forget some hazards, then your result will also be less accurate. So it works best if you have lots of independent actions, like customers in the supermarket or packets on a network. If you have long sequences of dependent actions, like a long program that's executing with very dependent, then that is not modeled directly by ΔQSD. Okay? You would have to model that as a single component. If they're really dependent, then it will not be as accurate. Okay? And the final thing, you have to compute. You have the CDFs, you have these cumulative distribution functions, which is a complicated thing. It's this function, you can approximate it, but it's a lot of data. So you have to compute with CDFs. So by hand, it's usually too hard. You have to use computation computers for this. But still, it's good, because other techniques, for example, simulation, is even much more costly. See, you're not actually simulating behavior, you're summarizing it using stochastic techniques. Okay? So on a laptop computer, you can actually compute fairly large designs. So you will see in the lab session a little bit of that, get some taste of what you can compute. Okay? So we are working on a software design tool using this. So this is still kind of work in progress. So this is actually a technique that has been developed over more than 20 years, and that we are making into a full-fledged approach. But there's a lot of practical experience. So everything I'm telling you has been tested on real industrial systems. Okay. So this is just the introduction. Okay. How do you measure delta Qs? How do you diagnose? So what kind of Sherlock Holmes techniques you need? More ideas on timescales and shared reduces. So the dependencies part is still kind of not finished. The website of PNSol has actually a lot of documentation, but it's kind of really scattered. But still, it's quite interesting. Okay, so we have a project on this, and so we're looking for PhD students. I'm also looking for master student, final year, travail de fin d'études, project for this. So this is a project with the company PNSol in the United Kingdom. Okay, so let me stop here. So I'm a bit early, but that's okay. So I stop here.